So we've been talking about energy involved with state changes. So this is a heating curve for water. And what's shown here is starting with ice at minus 25 degrees, adding heat. And this is for 1 mole of water. So you add heat to the frozen water and it warms up until it gets to the melting point. At the melting point, the temperature will not increase until all of the ice has melted. Once all the ice has melted, then the temperature goes up again until it gets to the boiling point. At the boiling point, the temperature remains constant until all of the water has vaporized, and then the temperature will go up again. So we need to be able to calculate how much energy is needed to take a substance from one temperature to another temperature. And the best way to approach that is to sketch out a heating diagram or a heating curve and identify where you're starting and where you're going to end up. Because sometimes you'll be ending up like at 75 degrees Celsius and you're going to start at 0 with frozen water. And so you need to be able to figure out where you're starting and where you're ending up. For this one where we're going to do this whole thing, each of these line segments is going to be one calculation. So the slanted lines are Q equals MC delta T. We learned that back in chapter 6. So you need the mass of the substance and its specific heat capacity, and then you can use the curve here to get the temperature change. This first line segment, we're going from minus 25 to 0. 0 minus negative 25 is plus 25. When you get to a flat place, you're going to use either the heat of vaporization or the heat of fusion. This is melting, and so you'll use the heat of fusion. And you'd multiply by the amount of substance in moles. Then we've got another temperature change part where you use Q equals MC delta T. Specific heat capacity for a substance in its liquid state is generally different than in its solid or gas state. So you have a different specific heat capacity. And then on this big horizontal place here, that's the heat of vaporization, again, times the amount of substance. And then, again, Q equals MC delta T over here. So this is showing us sort of a picture of what's going on. We've got the ice warming. When you do the calculation, which we're going to do on the next slide, this would be 0.941 kilojoules for 1 mole. The ice melting would be 6.02 kilojoules. The liquid water warming up, 7.52 kilojoules. The liquid water vaporizing, 40.7. And then the steam warming, 0.904. To find the amount of energy needed to go from the very beginning to the end, you would just add them all together. So any questions about the big idea? So here's an example. And this is doing that calculation, but we're going to actually show it. So calculate the amount of heat needed to take 1 mole of ice at minus 25 degrees Celsius to steam at 125 degrees Celsius. And we're given specific heat capacities and heats of vaporization and heats of fusion because you don't memorize those. The only one you might memorize or remember is the specific heat capacity of liquid water. So before we start something like this, we need to sketch out a heating curve. So we've got heat being added here and temperature going up there. You need the correct shape of the diagram. The slopes and the lengths of the lines don't matter. So we're going to identify where we're starting. We're starting at minus 25, and that's ice. So this horizontal line is melting, so this is the ice. So we're going to start at minus 125. And then we should know the melting point of water is 0 degrees Celsius. And we can label this temperature up here, because this is where water boils. What temperature is that? 100. So you should know those for water. If it was a different substance, they'd be provided if it was an exam, or you could look them up. And then our final temperature is 125. So that's above 100, up here somewhere. So we're going from here all the way up to here. We're going to do all of the different line segments. I'm just going to label these with letters because there's going to be so many numbers on this slide that we don't want to get them lost. So we'll have a separate calculation for each line segment, and then we'll add them together. So for A, we're taking ice and we're warming it up. So that's Q equals MC delta T. If you can't remember, am I supposed to use heat of fusion or Q equals MC delta T? If you try to use Q equals MC delta T on this line segment B, the change in temperature is going to be 0, and so you're not going to get anything. So it won't work. But it will work here where you've got a temperature change. So Q equals MC delta T. Well, what's our mass? They didn't give us a mass. 1 mole of ice, right? Ice is water, right? So we have to calculate how many grams. So you can figure out the blanking there. Molar mass of water. And the math there is very challenging. 18.02 grams, right? So we've got 18.02 grams. And then we're going to multiply that by the specific heat capacity. We've got to use the correct one. This is ice, so we're going to pick out the one for ice, 2.09 joules per gram degrees Celsius. Always write the units. And then here we've got the temperature change. So delta T is always T final minus T initial. So for line segment A, what's the final temperature? 0. And what's the initial temperature? Negative 25. So that's a positive 25 degrees temperature change. Signs matter for the temperature change. So 25 degrees Celsius. So the degrees Celsius cancel and the grams cancel, and we're going to get energy in joules. So I'll just apologize to the YouTube people. I'm going to be coughing and clearing my throat a lot because California is on fire and the air quality is really bad. So 941.545 joules. Just as a sig fig exercise, I'm going to assume that these temperatures are exact. The 0 and the 100 are. Okay, anybody else see this? Yeah, well, if you see me doing stupid stuff like that, you're supposed to tell me because, yeah, it's not minus 125, it's minus 25. There, that's better. We're going to pretend that those temperatures are exact, and so then our value here should have 3 significant figures. And we're not going to round it yet because we're going to be adding a bunch of stuff together. So any questions about that one? So then, line segment B, this is the ice melting. So that's where we use the heat of fusion. We have 1 mole of water times the heat of fusion, 6.02 kilojoules per mole. The moles cancel out and gives us 6.02 kilojoules. It's easy when you're doing 1 mole. So for line segment C, what equation are we going to use? Q equals mc delta T? Because the temperature is changing again. Well, the mass of our water is the same, because melting it doesn't change its mass. Specific heat capacity now, though, we need to use the one for liquid water. So 4.18 joules per gram degrees Celsius. And what's the temperature change for line segment C? It's 100, because we're going, the final temperature is 100 degrees and the initial was 0. So 100 minus 0 is 100. So grams cancel, degrees Celsius cancels. 18.02 times 4.18 times 100. $7,532.36. Again, this would have 3 sig figs because of the specific heat capacity. What's the unit on this one? Joules. The units are important here because the heat of fusion came out in kilojoules, and these are coming out in joules, and we need to be aware of that when we add them. So line segment D, now we're converting the water from a liquid to a gas, or boiling, vaporizing. So we're going to use the heat of vaporization. We have 1 mole of water. We're going to multiply by the heat of vaporization, 40.7 kilojoules per mole. The moles cancel. 40.7 kilojoules. Now we've got one more piece. We're taking that steam and heating it up. Q equals mc delta T again. The mass is the same, but the other values are different. 18.02 grams. Now we're going to use the heat capacity for steam. 2.01 joules per gram degrees Celsius. And what's the temperature change for this one? 25, because we're starting, the final is 125, we were starting at 100. 125 minus 100 is 25. Degrees cancel, grams cancel. 18.02 plus, no, times. 2.01 times 25. 905.505 joules, 3 sig figs. Did I do something wrong? No. One of the common mistakes students make is instead of looking at the temperature change for the individual line segment, they'll use the total temperature change for all of the calculations, and that obviously is going to get you a wrong answer. So you're looking at each line piece individually, and then we add them together. So now we've got, we're going to get to the adding together part. We can't add joules and kilojoules. So 40.7, that's a big number in kilojoules. And so I would prefer to convert the joules into kilojoules because our answer is going to be more than 40 kilojoules. And that would be too big if we express it in joules. So going to kilojoules, we're going to divide these by 1,000. So this is 0.941545 kilojoules. This is 0. No, not 0. 7.53236 kilojoules, and this one is 0.905505 kilojoules. Yes?
On a test, if you get it joules?
On an exam, if you converted them all to joules and added them up, that would be fine. You might have to convert that to kilojoules if all the multiple choice answers are given in kilojoules. But if this was a show your work problem, either one would be fine. Unless the problem says kilojoules. Yeah. Otherwise, if you wanted to convert this into calories or something just to make it difficult for me to grade, you could. I don't recommend that, though. So we are taking 0.941545 and 6.02 and 7.53236, 40.7, and 0.905505. We're going to add all those together. What did I do? Trying to be fancy on my calculator, and on Monday morning that doesn't work so good. Okay, start over. Do it the hard way. 0.941545 plus 6.02, 7.53236 plus 40.7 plus 0.905505 equals. Anybody else get this number?
Yeah.
Awesome. Either we're all correct or we're all screwed in the same way. Okay, sig figs. We're adding here, so we're looking at decimal places, the fewest decimal places. So this one has 3 decimal places. How many does this one have? 2. I didn't underline anything because that didn't really come from a calculation. I mean, it kind of did, but so this would have 2. How many does this one have? 2. Okay, let's stick to English because my brain is scrambled enough. How many does this one have? 1. Thank you. Uno. How about this one? 3. So the smallest is 1. So we should round our answer to 1 decimal place. And so this is going to give us 56.1 kilojoules of energy. Any questions?